And I'm going to pause the key for me to teach my Okay? Any question about it then too? Everybody clear? Yeah. And then it's also 100% phone and 25%. And I have 48 hours policy again. And office hour tomorrow and on Friday, John is the office hour, right? And Monday is a holiday, so Tuesday I have office hour. It's the same time from 10 to 11, but it's on Tuesday. Go in the same room. Now if you I'll be there. And then Tuesday afternoon, coming is regular hour. So this is office hour before the exam. So you can go to our office hour if you have questions. Any questions? Right, so I always use the same so hopefully today I can finish my visual system lecture. But on Monday I already talked about several things about visual system. I always went through. The most important thing is I told you that there's this dark current, right? So you remember I talked about dark current. Those are photoreceptors. That is a dark current here. And then how do you, so when you don't have light, then actually you have this current because there's a channel, G protein, and exactly the Npb gave the channel open. So now your sodium is going, so that's constantly have this dark current. And then when you have light shine on your photoreceptor, you shut down the current. So this is fundamental for your photoreceptor. Don't ask me why, that's the way it is, biology. So when you don't have light, you have more neurotransmitter release because when you have a sodium going, you depolarize your photoreceptor. So when you don't have light, while you are sleeping, you have this dark current. So your photoreceptor actually releases more neurotransmitter. That's relatively speaking. As I told you, the photoreceptor by itself doesn't have those two elements. So it doesn't have action potential, but it depolarizes the membrane potential. And then when you have a light, actually you release less neurotransmitter. Okay, so that is fundamental. It's a biology. Okay, so which is very interesting. All right, so that's the very first thing. And how do you, when you hit the light, how do you get this? So I went through this on Monday as well. So this is very important, fundamental, and I also asked the question for tomorrow's discussion as well. So like how this pathway, photoisomers and trigger this transduction, which is, I told you, transduction is just like a G protein. G protein comes from receptors, I told you, right? So that this is just like that, and then when you activate it, then you ATP bind, activate our phosphodiesters, then you hydrolyze cyclic DNP, then you close the channel. So this is very classical fundamental pathway. It's been studied for decades, so I think this is very important signaling pathway. I want you guys to be able to at least understand that. All right. Okay. So now, and the last slide on Monday, I told you there's optogenetics, and after the class, some student asked me what's optogenetics. So, I mean, in my class, I try to give you some things that is more updated in neurobiology. Of course, I won't cover this slide in the exam, so don't worry about that. But if you heard about optogenetics, because that's the things in the 21st century that you need to notice. Optogenetics is a way that for scientists to be able to using fiber optic, using light, to stimulate those neurons inside your brain, in this case it's mouse, so that you can increase the neural activity or decrease the neural activity, allow you to see the behavior change, which is very, very kind of powerful method, allow you to study a lot of biological questions. So that's why this is terminology, just like connectome, right? So I give you this term. All this term is for 21st century neurobiologists, so you need to know this. I hope that some of you will become a neurobiologist in the future, so that's a great discovery. And for that, I think that you need to know this term, even though perhaps I won't give you a test of that. And the important thing about this optogenetics, I told you that they're using the same things about the rhodopsin, but it's not metabotropic. It's ionotropic. So you don't call it rhodopsin, you call it channel rhodopsin because it's ionotropic. So this is a very fundamental discovery, allow you to be able to do all these kinds of things. Okay, so So that is what I mentioned on Monday. Now, the important thing that I'm going to continue to discuss is the pathway. So now how are you going to pass information from your photoreceptor all the way to go to your brain? So we have quite a few pathways. So the very fundamental thing is this. So the very first thing I want you guys to know is for the pathway, there's this functional pathway we call it on pathway and off pathway. Right? And this is, I call it functional because, how do you know that? Because scientists need to stick electrodes into the retinal ganglion cells because, like I told you, in the system, only retinal ganglion cells start to fire action potential. Your bipolar cell will not fire any action potential either. So it's your retinal ganglion cell will fire action potential. So when you have light, your retinal ganglion cell fire more action potential. We call it on pathway. Alright? So when you don't have light, meaning it's dark, your retinal ganglion cell fire action potential. Yeah, it's dark, but your retinal ganglion cell fire action potential. We call it off pathway. That's the very first thing that I want you guys to be familiar with. So it's a functional. When your retinal ganglion cell fire action potential and then all the way down to all the way to your brain, everything will have action potential, right? So that's on pathway. So if it's light, there's light, then this fire action potential, we call all the pathway all the way to your brain. It's on pathway. But if it's dark, and then you fire action potential, then we call it off pathway. So these two pathways in our system is very interesting. They are inherited, and it's parallel. Okay? Cannot separate. You cannot separate it. Right? So just inherit. In your system, you have this distributed along your everywhere on your retina. You have on pathway and off pathway. And these two pathways, why biology want to have this, I don't know. But these two pathways allow your brain to be able to understand and appreciate whether there's a light or there's no light. For scientists, in order to be able to study that, then they need to have a method to stimulate that, right? So that's why there's this, we call it light source. And again, this turned out to be the concept of receptive field, which is I show you that somatosensory system is very easy. It's on your skin where you touch with the neuron fire action potential. That is that sensory neuron's receptive field. Here, the receptive field for the visual system is whether you have a light source. You can shine the light on the spot, like this joint, here light. And this is the connection from photoreceptor all the way to your retinal ganglion cells. So what you want to look at is that whether these light sources are able to stimulate this retinal ganglion cell or not. So it turns out this light source can be these two patterns. We call it central illumination and angular illumination. So you can see that in this cartoon it shows that there's a spotlight in the middle, or in the center is the dark. Yeah, you see this? So the angular, the reason we show it angular is because surroundings we don't have kind of bright light. So that's angular illumination. Okay? So we call this the center, we call this the surround, which is, I'm going to come back again later. So what is surround? Meaning that the center is this. You see this? Center? The surround is right next to it in a circle. So basically the surround is those that directly stimulate the neighboring photoreceptors. Okay? So that is the stimulation. And you can ask, why is it only single spot? Why there's no surround? Of course there's a surround. It's just dark. Yeah? So the surround is the dark. And when it's dark, you don't show it. Right? So basically this is the concept of receptive field for your visual system at the retina level. So it's like you using this spotlight, that's what we call it, because all this spot is very small. You try to control it. So when you're doing experiment, you can make it smaller and smaller, and then to see whether you can get the maximum stimulation so that you can have that spot. Or we give you this surround light so that you can see whether you have a strong action potential or strong inhibition, meaning less action potential. So this is very important concept. Now, that's why I'm using this cartoon to show this again. So center, surround. So you have two ways of stimulation, right? You can have a center of light, surround is dark, like this, or center is dark, surround is light. So this is two different ways of stimulate. And you are asking questions when you apply this. How is retinal ganglion cell fire action potential? Yeah? So in order to do that, then we need to introduce another pathway, which is anatomically. We call it direct and indirect. So what is direct? From here all the way down to your ganglion cells, that's direct. What is indirect? From the side, yeah, from your neighbor, through these horizontal cells or hemacrine cells, go to your retinal ganglion, which is in the next slide that I'm showing you here. So I call this anatomical, meaning this is another pathway. It's describing the connection in your retina that from the light source from your photoreceptor to bipolar directly to this retinal ganglion. This is a straight line, light coming in, this straight line. This we call it direct pathway. For those, if you shine light on the neighbor cells, neighbor photoreceptor, and then through these horizontal cells or hemacrine cells and come to retinal ganglion cells, we call it indirect. Okay? So that's why we have a center surround concept. It's whether the light is stimulated right on me, or light is stimulated surrounding photoreceptor and through indirect and come to me. Yeah? So this is indirect or direct pathway. So this is on pathway, off pathway, and direct, indirect. One is functional, one is anatomical. Now, for this direct and indirect, yes, with this fundamental concept. Indirect connections always is inhibitory. In other words, it's always opposite. When this indirect, for example, coming to its own direct, is excitation, then come here would be inhibition. If your indirect, this neighboring photoreceptor, it's inhibition of your retinal ganglion cells. Then you come to this retinal ganglion would be excitation. So that means opposite. Okay? So the indirect pathway always is inhibitory. Depends on whether this one is excitatory or inhibitory, then you opposite. Okay? So that's why there's this center surround concept. When your center is on, then the stimulation on the surround will be off. Yeah? And when your center stimulation is off, then the surround will be on. So that is the major concept about indirect pathway. So now, why you have this? Why you want to go to all this trouble for your system to have this? Because I have no idea. I don't know why. But at least we know how this works. Because all your photoreceptors with light have less neurotransmitter, without light and more neurotransmitter. And how can you reach that? With on pathway, you have more action potential on your retinal ganglion cells. With off or dark, you have less action potential on your retinal ganglion cells if you are on pathway. So there's this very fundamental biological question to do. So it turns out that scientists study that, they figure out, so again, this is a cartoon to show direct pathway, if the light shines directly to this, right? Photoreceptor, bipolar, and retinal ganglion cells. But you shine on the peripheral and through this horizontal cell, you go here, then this is indirect. So it turns out that for this synapse, it's amazing that some of the synapse is sign conserving, and some of the synapse are sign reversing. So it turns out, for your every single photoreceptor, you have multiple bipolar to connect to it. All right? And here, this is the cartoon I'm going to show you. The next So it's direct, indirect. Right? So it turned out that for you, every single photoreceptor, as I showed you, there's more than two. There's a multiple. But it turned out that there's these two types of bipolar cells are able to connect to your photoreceptors. All right. So the synapse are different. For one type of synapse, we call it sign reversing. What is sign reversing? Meaning that it will. So what is the sign? So that means membrane potential. Sign reversing is when your membrane potential from your photoreceptor are depolarization, then your bipolar will be hyperpolarization. Yeah? Yeah? What is sign conserving? Meaning you conserve the same change. So when you depolarize, then this will be depolarizing. Okay? So this is fundamental, so that when you can imagine that when you have a light, I told you that when you have light the photoreceptor, what happens to neurotransmitter? You have less neurotransmitter. Why is that? Because your photoreceptor hyperpolarization, right? And because in hyperpolarization, if it is a sign reversing, then what happens to this bipolar? Sign reversing. So this bipolar cell become depolarization. That's good. Depolarization. So what happens to your phylomoaction potential? Yeah. So that's light. So we call this is arm pathway. How about sign conserving? Light. Photoreceptor hyperpolarization. Oh, it's a sign conserving. So then what can you do with your bipolar? Hyperpolarization, which is less neurotransmitter. So start file action potential. With light, I don't want to file action potential, so that's off pathway. Yeah? Okay? So that's why on pathway, off pathway, on pathway, off pathway. So it's the same kind of analogy. Now you have dark. It's the same thing. For the dark, so now you depolarize, right? Because your channel, dark current, depolarize. Sign reversing, what happened to this? Hyperpolarize. So you less action potential. Dark. So your retinal ganglion cells fire less action potential. So this is on pathway. Yeah? Okay? So now if it's dark, you depolarize, sign conserving, depolarize, fire more action potential. So it's dark, so this is an off pathway. Yes?
It's just picking one of these, though, to follow, right? If you don't have
All right. No, it's in your system. They are both. They're multiple. So that's why I say on pathway and off pathway is integrated into the system. They are parallel. Okay? Every single photoreceptor, they are multiple. Some of them are on pathway, some of them are off pathway. Multiple bipolar cells to connect with it. Okay? Because you can imagine that your retina is like tons of photoreceptors, tons of bipolar cells. It's not only one-to-one. It's one photoreceptor and multiple bipolar cells connect to it. Some of them is sign reversing, some of them are sign conserving, allow you to have this on pathway and off pathway. Okay? So final question is, why do you have this? How can you have sign reversing and sign conserving? Right? So that is, so what's the neurotransmitter here? So the turn out the neurotransmitter is glutamate. So the mechanism we know that already. The reason this is sign reversing and sign conserving is because they have different receptors, different glutamate receptors, allow them to be able to have these differences. So what are they? So come back to our old story. One is metabotropic receptor. You know that, right? So what is metabotropic receptor? So by itself is another channel, but you signaling and affect other channel. The other one is ionotropic receptor. All right, good. By itself is the channel. So for your sign conserving, not all pathway, it turns out because it's glutamate the receptor are AMPA or KNF. Yeah, AMPA or KNF receptor. Because AMPA and KNF, as you guys already learned this, they are channel. So when you have a glutamate, they open the channel, allow ion to go through. So that's why this is a sign conserving, because you have a more neurotransmitter, you have more depolarization. You have more neurotransmitter because you have more depolarization. You have more neurotransmitter, you depolarize. So that's sign conserving. So that's why it's off pathway. How about on pathway? How does it work? So it turns out the on pathway is opposite. When you don't have too much of a glutamate, for example, have light, yeah, so you hyperpolarizing a photoreceptor, you have less neurotransmitter, then by itself, then this channel is a happy. They open this channel, allow ion to go through. So this is when you have light, so your photoreceptor are hyperpolarized, so you don't have neurotransmitter, but your bipolar cell have channel open, so that you depolarize it. So that's sign conserving. When you have glutamate release, that's when it starts. You have more glutamate release, what happens? To metabotropic Z protein go here to shut down your channel. Yeah? Through signaling, shut down your channel. So you don't have current. So that's why it's sign reversing. Okay? So that's the mechanism. That's a very fundamental way. I integrate all the knowledge I showed you before, so I hope you can understand how this is work. So that in your system, you always, when your photoreceptor, you can connect to multiple bipolar cells. Some of the bipolar cells to retinal ganglion cells is on pathway. Some of them to bipolar cells to retinal ganglion cells are off pathway. That's why I say these two pathways are integrated, right, in your system. Okay? Very important. So now, because of that, now you understand on pathway, off pathway, direct, indirect. Indirect always is opposite to the direct pathway. Then there's this important concept. This is not only in the visual system, but also in all the sensory system. We call it lateral inhibition. So what is lateral inhibition? So if you are centered, you have surround, right? So lateral meaning is in the surround, in the visual system. But in the sensory system, the lateral meaning next to the stimulation. That's lateral. So the same concept. So your sensory system are actually trying to help you. When you have a certain stimulation, go to your whatever sensory system, what you want to do is try to inhibit your neighbor so that you can move forward, allow you to move forward. Why you want to do that? So that your sensory system can focus on the right spot. Does that make sense? So in a way, your sensory system already has this mechanism allow you through this lateral inhibition, just like I used in this football, that this player want to move, or this guy carry this football move forward. If you have your teammate help you surrounded to press other people, you can move faster. Yes? So that's exactly the same thing for your system, your sensory system. It's like if your direct pathway is excitation, and then for it to influence other pathway, it will be inhibition. But if you are inhibition, I mean sometimes because of on pathway or off pathway, there's light and dark, so that if this is inhibition, then what happens? You will excite others. So you want to make sure the pathway surround you has the opposite response, so that you can distinguish your response. Yeah? So that is the fundamental concept we call lateral inhibition through direct, indirect pathway. So in here, I try and just to use this example. I ask, okay, so if this is direct, so this is direct, this is indirect, right? So you have a synapse here and a direct. This is retinal ganglion cells, and then you have synapse, retinal ganglion cell here, retinal ganglion cell here. Then I'll ask this question: you shine light on the photoreceptor. So very first things I need to tell you is always this: whether this is an on pathway or off pathway, because this is different. So this is a given. I always tell you, okay, so how about this is ARM pathway? If this ARM pathway, there's a line, what happens to your retinal ganglion cells? Fire action potential. Fire more if it is I. So if I tell you this is off pathway, then what happens when you have line? You have less action potential, so you can write on negative or positive, negative. Sometimes it's just relative. Okay. So now this is ARM pathway, so the red pathway will be positive, then you are exciting. So then for this go indirect to the neighboring retinal ganglion cell will be inhibition through indirect pathway. Okay. So this is these two questions I told you. So that this is ARM pathway, so this is excitation, and it will be inhibition. Okay, so I ask you excitation, and the neighbor will be inhibition. So it's positive, negative. The positive, negative is a relative term. Okay, just more action potential, less action potential. In a way, this is the visual system that, as I explained to you earlier. So with this, then I'm going to use this. I'm going to show you how lateral inhibition works. What is lateral inhibition? So basically, lateral inhibition allows you to see the junction between these two. So, for example, in the visual system, it's more like there's a light, there's dark, in between. That's more important for your biology, right? So, for your visual system, if you have a light, if you have a dark, you want to see the edge better. Yeah? If you can tell the edge better, then you can distinguish things easier to see the border so that you won't fall into the cliff, yeah? Things like that. So in order to do that, then using this lateral inhibition can easily explain why this is work. So let's say again we're using ARM pathway. Okay, so let's use ARM pathway as an example. Now, as I show you here, with light, direct is excitation, indirect inhibition. So it's the same like this. All this is retinal ganglion cells. Retinal ganglion cells. So this is showing action potential. So that's the response. The higher, at the top is higher, more action potential. The lower is less action potential. So now, for all these retinal ganglion cells that are under the stimulation with light, so if they are all ARM pathway, then what happens? So they will look like this, right? Excitation, 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 excitation. But there's a lateral inhibition, lateral inhibition, lateral inhibition, like this. So every single retinal ganglion cell, they will receive one major excitation and two inhibition from neighbor. So of course it's more than two. I mean, just cartoon diagram to show you. So overall, you have a certain response, yeah? But because they all are within light, so they all have the same response along this retinal ganglion cell. So that's the response here. Okay? How about dark? So when you have dark, now this is ARM pathway. Dark, what does that mean? It means there's less action potential, so we use negative. Less action potential, so it's inhibition. However, the indirect pathway will be what? Excitation, so it's positive. So that's why in the dark, positive. So now you receive one negative, major, two inhibition, two excitation. So overall, there's this label. But compare this one to this one, which have a higher action potential and more action potential. This one, right? Because of the excitation, this is the major. So that this guy here have a higher response than all these guys under the dark here. So that's comparison. So that is the normal difference. But because of lateral inhibition, it turned out that at the edge, meaning that the region, the photoreceptor or the pathway right next to this junction, so there's one pathway here, one pathway. There's something magic happen, which is for this one. Okay, so this one is showing the direct pathway just right next to the edge. Okay, so that's what I mean here. So now you can see this guy are receiving retinal ganglion, so this is excitation, of course, because you still have light. And then you are receiving inhibition input from this side. However, on this side is different, because this guy are inhibition. So instead of inhibition is coming, is excitation is positive. So for this particular retinal ganglion cells, right next to the edge on the light side, actually, they receive more excitation. There's another positive instead of two negative, right? So now their response are higher. Okay, for that one. On the other hand, for the one that right next to the junction, but is on the dark side, what happens? On the inhibition, I receive excitation like this one, but on this side, I through this, it's inefficient. So I'm more inefficient. So what happened? Oh, less response. So what happened to the junction? You exaggerate the differences. Compared to all others, the differences from here to here, so I show you here. Now you exaggerate, so that's seeing the edge. Okay. Allow you to be able to see the edge better with your system. So this is inherent. You don't even need to think. They do that for you. So now it's through the beauty of lateral inhibition that you are able to do that. And this is not only in the visual system, but also in the sensory system or other systems. They all use that. So that's why lateral inhibition becomes a very universal concept in a lot of systems when you think about sensory regulations. To allow you to be able to see the difference. When the stimulus is the same, and it's one thing, but you have a difference, that allow you to be able to see the edge of the difference, which is crucial for your system, right? So you want to be able to tell those things easy. All right. So for that, now I explained to you for the light source, we have a center and surround. So it turned out for the receptive field for your retinal ganglion cells, scientists study. So it turned out that they are able to figure out this receptive field. Now we call it center surround receptive field. So it's for on pathway. Now you can show that. Now this center is on, surround is negative, inefficient. What does that mean? That means if you shine light on the center, for that retinal ganglion cell, you fire action potential. If you shine light on the surround, surround, only on the surround region, then you inhibit that retinal ganglion cell. So that we call it on pathway. And the reason is why we can make a diagram like this is because in theory this is more like this. Because your photoreceptor, if you look at the retina just right on the surface, then you will see this is the photoreceptor, or this is the photoreceptor. This is the surround, this is the center, right? So that's why scientists draw them like this. So that's a center surround receptive field. So this is the on pathway. Okay. So of course you can also have an off pathway just like this. So this is on center, this is off center. So it's negative. Yeah? So off center meaning when you shine light in the middle, it is your retinal ganglion cell won't fire action potential. Yeah? So that's off center. But it's back, then your retinal ganglion cell fire action potential. So that's and the reason I want to show this is the same because this is the same concept. And I want you guys to look at the YouTube, which is the next lectures. There's a Hugo and Wiesel classical experiment. When they did that, they show this instead of they show this. It's the same concept. They just show this is on-center, so all this cross is a positive, and then this is negative. But basically the same concept. Instead of drawing like this, they like to draw receptive field like this. But it's the same concept. It's just the different way of showing it. And now we all use this way to show center surround. Of course, I told you that this is a spotlight. So you shine light on this. But there's an area, right? So even if it's a spotlight, you can even make it smaller, right? Yeah? I mean, it's just you can use a shutter to control the light. You can make it smaller. So when you are doing stimulation, you can control so that the light is control all cover everywhere. Or you can have a light control only partial of that. So by doing that, you can have a stronger stimulation or less strong stimulation. The reason is because it depends on the area you cover. So you can see all those responses. Okay? And then you can also shine light on entire surround. or just portion of the surround, so you can see all these response. Okay, so that's another thing I like to tell you. Finally, for this. So far, the pathway I'm discussing is in the retina. By your visual, actually, there's all these pathways connect all the way to your brain, especially in the first class, we call it primary visual cortex, right? And before that, actually, going to this region, we call it lateral genetic nucleus. Lateral genetic nucleus. So that is the very relay from your retinal ganglion, which is part of your thalamus. Remember thalamus? What is thalamus? Now when we talk about spinal thalamic pathway, it's your sensory system will pass information all the way to your thalamus. So thalamus have all these different nuclei, alright? So one of the nuclei we call lateral genetic nucleus, that's more important for your visual system because that's your relay for your visual system. And other nuclei is responsible for others, for example, somatosensory system and others. Alright? Now, first thing about the pathway of our eye is, everybody maybe all knows that our eye position is like this, right? Yeah. So have you ever seen fish, also especially some fish, your eye position is this, right? Yeah. And if you look at mouse, mouse's head is more like this. So their eye position is angled, right? So different species, actually, their eye positions are a little bit different. But their visual system is so amazing that they all follow the same rule about somatosensory system or other sensory system or motor system. That is, your right visual field, the information go to your left brain. Left visual field go to your right brain. How are you going to do that? How are you going to do that? So, in order to be able to do that, then your eye, all those retinal axons need to spread. Alright? So this is a cartoon to show. So again, one thing is very important because a lot of students are confused by this. So there's a term called visual field. Alright? Visual field. What is a visual field? Visual field is the outside world. The outside world you are seeing.